In this video we have one application. We have an open box having a square base. It's constructed of 108 square inches of material. What should be the dimensions of the box to obtain a maximum volume? So this will be using the idea of relative maximum in this case, using critical numbers, first derivative test. If you want to try it, go ahead and pause the video, and then I'll be right back. So here's the main information that you have for this. It tells us that the base is square, so if I let x equal the length of one side of the base, then of course all the sides are going to be of length x. So I'm letting x equal length of the sides of square base. We'll let h be the height of the box, and it is an open box, so it has the sides, the bottom, but no top. The surface area is given to be 108 square inches, so that's the total. So we can set up an equation. The area of the base, of course, since it's a square, is x squared. And the area of each side is, one side is x times h, but you have four of those. So this x squared plus 4xh represents the surface area. And then we have the volume over here, which is what we want to maximize. Volume is equal to the area of the base, x squared, times the height. And of course it would be nice to have the same variable here, one variable. So let's take this equation here and solve it for h. Bring the square x squared over, and that's going to equal to 4xh, and then we divide by 4x. So h in terms of x will be 108 minus x squared over 4x. So this is what we have for h, and then of course I want h to be a positive number since we're dealing with dimensions and so forth. So on this number line we'll plot the zeros of the numerator and denominator. So denominator is 0 when x is 0, and if you solve this factors into square root of 108 minus x and the square root of 108 plus x. So I'm going to have zeros at the square root 108, and over here on this side minus the square root of 108. And this is approximately, square root of 108 is approximately 10.4. So we're talking the interval x is greater than 0. If I pick a number over here greater than, say, 10.4, let's call it 11, I'm going to get a negative number over here to the right of this. And if I pick a number, say, between 0 and 10, say 5, this will be positive. Not concerned to the left of 0, but it's going to be negative over here. So positive here and negative here. So this would tell me then that x should be greater than 0. I don't want it to be negative, and it could be somewhere less than or equal to the square root of 108. So whatever value we get for x should be somewhere in between there. Now we can move this here, and let's make the substitution now for the volume. This will be x squared times h, and now we have an expression for h. So this will be 108 minus x squared over 4x. And let's simplify, let's multiply through by x squared. So if I multiply this first expression here, 108 by x squared, and then divide by 4x, that'll reduce the x squared to x. And then 4 into 108 will give me 27. And then multiply the next one again. One factor of x cancels, so I'm going to get a minus x cubed here over 4. And that's the formula for the volume. Now we'll take the derivative of this then to find the critical numbers. And I should have an x right here. One factor of x cancels, but I still got the x there. So it's 27x minus x cubed over 4. So the derivative of that is 27. Derivative of 27x is 27 minus, and then 4 x cubed over 4, bring the 3 over here. This will be 3 over 4 times x squared. So the critical numbers come from numbers that make the derivative 0 or it's undefined. Well, here we have a polynomial expression, so it's going to be defined everywhere. So the only thing we need to look at is when is this going to be 0. So that's give us 27 then is equal to, take the 3/4 x squared over then multiply both sides by 4, cancels this here, and over here multiply by 4 and divide by 3. This will give me 36 on this side equal to x squared. Take the square root, get x equal plus or minus 6, but obviously in this case we're only interested in positive values here since we're dealing with length and area and so forth. So this is going to be 6. And then to confirm, let's see what we have here. Let's test it. Use the first derivative test. If I pick a number less than 6, say 0 or 1 or 2, the derivative will be positive. If I pick a number greater than 6, say 7, and plug it into this expression over here for the derivative, I'm going to get a negative over here. So the derivative is positive to negative, so that means the graph rises and then falls. If you were to graph this in a calculator, looking at the interval from 0 on up to about 11 or 10.4, which is the square root of 108, it'll look like a parabola. So this vertex right here is at 6. So the maximum value, relative maximum, in this case turns out to be an absolute maximum because it's in that particular interval. And what are we looking for? What should be the dimensions of the box to obtain a maximum volume? In this case we're looking for maximum volume, not area, maximum volume. So what should be the dimensions of the box to obtain a maximum volume? So x should be 6. And for the h, I erased that. So we have the formula h is equal to 108 minus x squared over 4x. So plug in 6 in where I have the x there, 108 minus 6 squared is 36, and then divided by 6 times 4, which is 24. And then we get h is equal to 3. So those are the dimensions of the box. So it's going to be 6 by 6 for the base, and the height will be 3. Thanks for watching. We'll see you next time.